Thank you very much. First of all, I'm sorry not to be there, but as you may imagine, more than 2 weeks far away from CERN, I would miss home. So I delivered the speech from here, and today we'll talk about this Monte Carlo workshop that we had, mostly on Fluka, and what we did mostly and what we did learn. So the talk is divided in 4 main chapters. The first one is a bit of a repetition of the very first presentation that I gave during the training week. So I hope that you forgot already the details, and the rest is what we did in these 2 weeks that I was there. So in the first meeting, I showed you how to install Fluka and Flare. What are the main characteristics of this GUI, and how to do the standard simulation that we use to check if Fluka is working, so the brag peak. And during the second meeting, I discussed a bit more about other Fluka features with a comparison with Gen 4 and a first simulation of the Kaon production. I have to admit that I'm not a Kaon expert whatsoever, so the presentation that we had previously was quite useful to me to understand what are the needs. So let's say take this presentation of today as a starting point from my side. And finally, I will list the area of interest and the open points. And so, for instance, the different discussion that we had about the line builder, how to use it for the muon production target, but also on the other side of the muon collider, so the detectors, so neutron guns for comparing the physics, muon guns to check the formal muons, and finally the Kaon production target. Now, why Monte Carlo? Monte Carlo because we have this very complicated problem, which is called the transport problem. How charge and neutral particles behave when they travel through the material. In general, this problem can be stated as we have a radiation source, which can be neutrons, photons, electrons. And we want to study how these propagating matters interacting with the materials, and extracting from this problem some quantities which can relate to the particle fluencies, the energy deposition, or interaction. So, for instance, the doses that are delivered to a certain material, or the displacement damage, which are caused by nuclear interactions. Now, this is not a trivial problem. And this is the Boltzmann equation, which in general describes this problem. So given a certain particle species, we can see how this evolves in a certain volume. So this is the integral form of the Boltzmann equation. And the evolution is mostly given by how many particles leave and enter the corresponding phase space. So typically the way that this thing occurs is through diffusion, so the first term, then scattering, the other second, third, and fourth, if you want, where particles can scatter in and out of the corresponding volume in the phase space, and finally we have radiation sources. The Monte Carlo approach is to take a single source particle, sample the mean free path until sample the free path until the next interaction. At the interaction point, sample the type of interaction and produce the secondary particles. You loop this until all the particles are below threshold, so they have small enough energy that such that we can assume that they are locally absorbed. And once we have done this, we are basically safe in the sense that we are simulating the whole history of a single particle. Now, what is the problem? The problem is that this works until we consider charged particles, because charged particles, they tend to travel and producing ionization losses and single Coulomb scattering. Now, what is the problem? The problem is that the mean free path between single Coulomb scattering and ionization losses is infinitesimally small, so it's extremely small. And the typical Monte Carlo code, such as Fluka, Gen 4, many others, they adopted the condensed history approach. So instead of simulating every individual Coulomb scattering and every individual ionization loss, we use the multiple Coulomb scattering theory. So we accumulate the effect along a certain step, and we accumulate this effect in a single interaction at the end of the step. Same thing for what concerns ionization losses. Now, In the Montecarlo, there is an enormous problem, which is how to track the particle, because sampling interaction is relatively simple once you have the cross section. The real challenge is to describe the geometry and to track particles inside of the geometries. I gave here two possible approaches. The first one is the Fluka one, which is using a constructive solid geometry. So it's using combination in the sense of unions, intersection, and subtraction of elementary bodies. Whereas in the Gent 4 approach, the approach is a bit more complicated from the implementation perspective, because it's hierarchical. So each volume needs to have a mother volume in which it is located. But this allows also more complicated implementation, in the sense of more complex geometry shapes, parametric, and in general, since you have the freedom of using C++, you can use loops to generate volumes. But let's go back to Fluka. In Fluka, there are four fundamental concepts: the concept of body, zone, region, and lattices. In principle, you need just the first three. So the body is the individual most basic geometry object. So can be a plane, a sphere, a cube, whatever you like. The zone is the intersection and subtraction of bodies. So can be still relatively simple composition of individual bodies. And then once you have the union of different zones, you get the region. The region is basically a portion of volume which is uniform in material. So, for instance, in this mu of the muon collider, you have different bodies, so the different planes to define the mu, and then the different zones, so the different intersection and subtraction, and finally one single region, which is the mu. And the mu is the union of the different bodies. Now, the lattices is a nice to have feature, which is basically the duplication of existing region, if confined in a single individual container volume. This is extremely helpful when we are working with accelerator constraints, because typically you have the same magnet, which is an extremely complicated object, repeated several times. So it's useless to define n extremely complicated objects. It's better to define it once and then copying it and pasting it in several portions of space. Now, since Fluka 4.5, we have a very nice feature, which is present also in other Montecarlo codes, which is the possibility of implementing CAD geometries. And this is extremely helpful for physicists, because we can exploit the works of engineers to implement directly the realistic geometries in our simulations without making any additional effort. So, for instance, in the left image, you can see a snowman. So the material of the snowman is plastic for the snow, graphite for the dark object, so the head and the eyes and the buttons, and the mercury for the nose. And we can see that some tens of 30 MeV protons are impacting on top of the snowman, and we can see the scoring of the energy deposition inside of the volume. This is extremely nice to have, because we don't have to model each individual object in a more complicated way. More realistic stuff, we have in this case, this is a tank for I believe target, or in any case with interconnect and sleeves. And we don't have to model all these small tiny objects, which are extremely time consuming, but we can just import them in Fluka. So this is something nice to have. Some of the discrete processes that we simulate, we have any kind of hadron, photon, electron interaction. And in particular, we have the low energy neutron in a point-wise way. So this is data-driven, which is extremely good. And this is a feature that is started with Fluka 4.2, so a couple of years ago. This is extremely important for any kind of activation study, any kind of study where the low energy neutron component is relevant. Now, that was for the discrete processes, which are relatively simple to model. The continuous processes are a bit more complicated. So the idea is that if we have even a single 1 MeV electron in matter, we have an enormous amount of interaction in a single step. So we don't want to do this. And therefore, we use the condensing story for ionization losses and the Molière theory for multiple Coulomb scattering. Now, the problem is that if we have a very rarefied, let's say, low density gas and very thin geometries, like for instance, the windows for the targets, this multiple Coulomb scattering doesn't work anymore, and we have to switch on back the single Coulomb scattering, which can be done easily in Fluka. Now, let's end with the introduction, and let's go in what we did in the first meeting. So the first meeting, the very first thing is to understand what are the Montecarlo codes that we are considering. So Fluka against Gent 4. Now, Fluka is not a toolkit. Fluka is, at the end, an executable, which you can run. Gent 4 is a toolkit. So Gent 4 is, if you want, a library that you can use to compile your own executable. And the reason why I prefer to use Fluka, besides the fact that I work in the Fluka section, so this is a good reason enough, but it has also the UI. So Flare is the graphical interface, which is extremely simple, extremely intuitive for new users. Now, the disadvantage that Fluka has is the limited support for detector implementation and some advanced framework, which is instead is present in Gen 4, and the final user directly sees this because it doesn't produce its own executable, but directly uses some more advanced frameworks like G4 Beamline or ILC etc. Now, the installation, you have to register and then download it for Fluka. So you need to wait 1 day for the approval. And instead for Gen 4, you have it's open source, so you have directly the source code. The installation process is relatively simple with Fluka. So you just download the binaries, you extract them, and you install them. Now, this is something that I learned last week. You can also have it on Lelix Plus, but it's a manual process, the approval. So first, you need to ask for the approval for the binaries, and once you have the approval for the binaries, you send an email to me or to my section, and we can give you access on the Lx Plus installation of Fluka. We do not encourage this too much because if many people use this in parallel, this could create process in the sense that everybody is asking the access to the same file at the same time in the nuclear database. And this is something that IT people didn't like. Gen 4 instead is a bit more complicated, as I said. You have to download the code, configure it, and make it. So, but this is very well explained in the guides and videos that you can find online. Now, let's start our first simulation. How we did it? We opened Flare, so we have the GUI open. And once we have this GUI open, the very first thing that we do is to click on input. We go on input and we start from the basic example. So here, new, you get the basic example. The basic example contains these cards because Fluka is a card-based code. So you don't have to code anything. You just have to specify which options you want in your simulation. So the very first card that you define are typically the default physics, some flare information, variable definition, etc. The second set of cards that are present are the primary particle information, so energy, position, direction, and how many of them. Finally, we have the geometry definition and material assignment. So in the geometry definition, we have the bodies, the region, and in the material assignment, you need to specify which material is present in which region. Now, for what concerns the example that is provided by the basics example, we have everything ready, but we have to change some things. In this first example, we have to specify that we want to have 100 MeV protons in water. So we specify the 100 MeV here in the card. We specified water in the assigned math card. And finally, we add a scoring for people that grew up with MCMP. It's called Telly in their language. And this scoring is a cylindrical mesh on top of which we score the energy density, the position. And this is extremely intuitive. You just need to specify the type of scoring, the particle that we score, so in this case, the energy deposition, and the mesh structure. Once we did this, we go on the Run tab, we run the simulation, and we check the Bragg peak. So this is the Bragg peak in the RZ plot, but most importantly in the longitudinal profile. So this is the usual plot that we are used to. And this is the comparison against Gen 4. So basically the results are fully within the error lines as we were expecting, because this is an extremely well-known process. Now, this is the end of the first meeting. So you have seen that basically we got a bit of a introduction with Fluka. The second meeting was a bit more advanced. So the very first thing that we tried to do was to run the same thing with Gen 4. I didn't ask I didn't ask you to write any code, just to understand what is the structure. The structure in Gen 4 is completely different. Indeed, you can see all these files that specify our simulation. And overall is roughly 1,000 lines. Most of the things were not written by me. I just took the example, the B1 example. The nice thing is that once you get the geometry done, you can specify all your parameters, not only all your parameters, many parameters of the simulation within one file, which is a macro file. And in the macro file, you have to specify also those mesh that you want to get. But then for the scoring and the plotting, you are on your own, because it just produces your CSV that you have to process with Python or whichever code you prefer. Let's go back to Fluka, some more advanced features. So the first one is the magnetic field. So as you have seen, the very first simulation was without magnetic field, in basically target in vacuum, which is useful, but is not let's say the realistic scenario. So in the top right slide, you can see the muon collider target station implementation, in particular the magnetic field. So there is this relatively big aperture of the magnets, which is constant. And the magnets are still able to give us 20 Tesla at the peak, and then it is going down in the tapering region, down to the chicane where the field is 1.5 Tesla. A second thing that I wanted to show you is the lattice replica capability with the basic photo lattice. So in this case, we have two elements, one dipole and one quadrupole, which are placed inside of a parking region. And then for the actual implementation of the line, I said, okay, given this complex element, which were implemented only once, let's create a lattice in the line. And the lattice is referring to these elements which are parked here. And for the simulation, the thing that you can test is to have a certain bunch structure in the transversal meaning, so certain beam size, and you can propagate it through the first dipole and then through the focusing and defocusing quadrupole. So you can eventually see the typical Betatron function also in a Fluka simulation, which is not done for, of course, for tracking purposes. Now, a second feature that I wanted to show you as well is the mgdraw.f. The mgdraw.f is the most general scoring routine that you can possibly imagine. And in particular is useful for visualization. So I wanted to observe the particle tracks. So all these lines are all the possible particles that you can imagine. But let's say that we want to be more precise. We can also exclude all the photons, electrons, positrons, and just getting the protons, pions, and kaons. We can remove the protons, we just get the pion and kaons, and we just get the kaons at the end. So you can see that out of 100 primaries, we had a massive amount of background particles and a single kaon at the end. So this is quite, for me, instructive to see how difficult it is to get a clean kaon secondary particle. Now, let's go back to the Kaon production target. I also started, let's say, a toy model for the simulation, starting from the muon production target. So I removed all the magnet, I removed everything, and I just kept this graphite target. And from this graphite target, we want to score what is the Kaon and pion yield, which is leaving the graphite target. So I said, okay, consider the surface between the graphite and the void, and score all the secondaries which are coming out of this say surface. And as you can see, the actual code, I mean, the actual cards to do this request is extremely simple. So one card per scoring, one for the plus, minus, and pion plus and pion minus. And this is the result. Given this very simple geometry, I consider two possible energies. The first one is 100 GeV, completely arbitrary, and the second one is 440 GeV. 440 would nicely match the SPS energy, and this is something that I mostly used, at least from the simulation that I did in the past. So as you can see, the dominant component is given by the pion plus and minus, but still we have this nice Kaon plus and Kaon minus that stretch down to hundreds of GeV. Now, this is what we did in the past, but I want also to discuss about other activities that were running in parallel, not, let's say, not foreseen before the meeting. The very first one was a discussion that I had with Paul, that now is here at CERN for the demonstrator. So now the line builder is a specific accelerator solution for the implementation of geometries in Fluka. Will be released soon. So at one point in summer, you will have access to the line builder. So it's something that it's very nice. It's a very nice thing to have. The idea is that given some elementary models plus the instruction set, so the instruction set is just the twist file for the people that work with accelerators, we are able to couple them together and get very complicated geometries without making the effort by ourselves. So we just have to implement the basic elements, and the line builder will take care of the placement and the magnetic field implementation as well. So you can see in the bottom left the Betatron collimation at LHC, but also in in this case I think it's the LCB. I'm not sure. So collision points in the LHC, and quite proudly the MDI of the muon collider. So you can see the different magnets inside of on the line and the detector as well. Now, an open point which was brought by Larry, Lawrence Lee, was that during a Maya meeting, Maya is the muon detector a muon collider detector. A different treatment for low energy neutrons was evident when one was deciding to use the physics list without the IHP at the end. So the problem is that the HP approach was exploiting the low energy neutron with the data with a data driven approach, so using data libraries. And the previous physics list was not doing this. So you can see, maybe it's a bit small, but there is a massive difference in the shielding of neutrons at low energy. And this brought us to do quick neutron gun simulation to test the Fluka versus HP versus non-HP physics list. And I can tell you Fluka is HP compliant because we use the same approach, which is much more precise, yet a bit slower. Now, a second point which was raised by Kai Kennedy and Tova Holmes was regarding the forward muon. The forward muons are of interest because they can be used to tag the vector boson fusion processes. Now, the problem is that the more energetic the muons are, the more radiative losses they are subject to. So in this case, you can see a muon going left to right, producing small electromagnetic cascades. because they typically generate hard gammas and hard electron and positrons due to these radiative losses. This was not a novelty. This was discussed also in the past, because the idea is that we want to understand how much we can measure outside of 6 meters of tungsten, which is our shielding for the detectors. So let's say that a muon is crossing 6 meters of tungsten. What is the energy at the end? Well, the energy at the end will have a certain uncertainty, which can be modeled as a Landau distribution. So the energy loss can be modeled as a Landau distribution, basically at any given incident muon energy, given that is above a few hundreds of GeV. So the tail is basically dominated by the radiative losses, the difference between the Landau and the actual tail. And this is something that we have to live with. So this can be an input for future detector studies. Now, let's go back to the Keon production target. One last thing before we go into detail. You can see that I set up a very, say, embarrassingly simple repository on GitHub. So if you want to check the files and check the results, you can go there. The Keon production target is a simple graphite target in vacuum, as with the same size and parameters of the muon production target to be consistent with it. And the keons are produced in the target and scored at the moment of the boundary crossing from target to vacuum. And I spanned through various energies from 10 GeV up to, in this case, is 200 GeV. And the idea is to see the behavior of the keon production and the pion production. So the pion production goes down when normalized by primary particles and by GeV, so at fixed, let's say, power of the proton driver, whereas the keon production is optimal at 20, 30 GeV. But this depends on the momentum cut that you apply, which I did not apply for this simulation. So this is something that has to be discussed and learned by the previous presentation. So the thing that we have to do for this work to continue, first to do a parameter scan on geometry and target parameters with maybe the parameters that were discussed before, and also implement the realistic geometry in Fluka, not just a target, to understand how many kaons can be, let's say, captured and exploited for the experiment, and of course the radiation and heat loss studies to guarantee the survivability of the apparatus. Now, the good thing is that I understand that you like to have a slow extraction, which is extremely good because it doesn't have any shock wave propagation, etc. But still, since we are talking about many GeV protons, we can have a bit of activation and these unwanted things, which can be studied with Fluke as well. And that's it. So I was relatively quick as promised. So I think that we can start the discussion from here.
Thank you very much. So I don't know if now we can also compare these results with what has been done in these other experiments, mostly for the BNL. Copio maybe was one of the closest to this setup. I don't know. Maybe they had a different target, but it looks like there is an answer. We can check the Fluke exercise again. And of course, the momentum of the kaons is an important aspect into account. Where these things are gonna go.
No, I just wanted. Oh, thank you. This is a very nice overview, and I just wanted to remark. I mean,
I don't know if it's me, but the mic is not really working.
might not be on.
Okay, then I get another.
I have another one here.
Now it's working.
Can you hear me now?
Perfectly.
Okay, excellent. Just a power cycle. Yeah. So no, that's a very nice overview, and I just wanted to mention that both for the Kodo experiment and Kodo 2, and also for Clever, we did actually do a lot of work with Fluka. for the Kaon production. And so, I mean, that definitely is something that, what is a little bit of an issue is that depending upon whether you're looking at charged or neutral kaons and what energy you're looking at, it's not always easy to benchmark because there's just not a lot of data in the world, right, that does this sort of inclusive production. So, you know, so that's maybe a little issue that we had. So what we found is that depending on, and we also have and Fluka, and you know, we found that in Jant 3 and Jant 4 and Fluka, and we found, I don't know, or something like that for, yeah, maybe even a little higher, depending upon what real big problem that really the benchmarking, right? It's not you might think because you know a lot of these depending again on the energy range you're looking at. If
So I'm afraid that also this other microphone is having some power issues.
sorry,
I'm afraid that it's cutting off every few seconds.
okay.
I'll give you another one because I
Okay.
think this one has some problem with the battery.
So as you know, in terms of the benchmarking problem, I think, you know, what I found is that if there's data from Shine, right? I mean, if it's like protons on carbon and it's interesting for, you know, kaon production for neutrinos or something like that, right? Then the data is there. And if you're, you know, and if you're looking at anything else like at higher momentum, you know, higher proton momentum or something like that, then you have to go back to data from, I don't know, you know, like the 1980s or before, right? And there might be very few points. So that was just the comment that I wanted to make.
No, yeah, I fully agree. Benchmarking with kaons is not easy at all. I mean, benchmarking we routinely do against Gent, against but it's still Monte Carlo against Monte Carlo. It's not Monte Carlo against nature. So I fully agree with you.
So you're saying that there is basically little point, well, as much a point as in comparing PT and Herbig, closer to what I do.
Well,
In comparing these two things, because it's simply that the data is missing. So whatever curve we're looking here, maybe even
yeah, I
let's
mean,
just-
okay, so I mean, just based on my experience, I would say that, you know, the results that you get from Fluke are reasonable for designing an experiment, for example. Okay, I mean, it'll give you a reasonable sensitivity, but you could never use the available Monte Carlo for hadron production if you were really sensitive at doing something for a really sensitive problem like evaluating a background or something like that, right? You know, where you're sensitive to the level of, you know, like say percent levels or something like that. As long as, you know, I mean, if it's off by 20%, then, you know, I mean, and it goes bad for you, right? Then, okay, you get 20% less statistics, but who cares, right? When you use it to design your experiment, and that's okay, right? You know, but it's a question of, like I said, the benchmarking, that's how the benchmarking problem shows up, in my opinion.
Yeah. No, I fully agree. I mean, Fluka is a wonderful tool to get your shape, to get the shape of the curves in this case of the yield. But I mean, most importantly, to get the simulation of the whole apparatus. So not to destroy anything in front of the beam, first of all. And I guess that I mean, you need to have some kind of magnets as well. So, for instance, in the muon production target, the limit is not a target per se. So the graphite will withstand the megawatt that we want to impinge on it. But the limit at the moment, it seems to be the surrounding solenoids. So yeah, Fluka is wonderful. I mean, it's wonderful for that because you can easily simulate the radiation load on everything in your geometry.
Right, and that also is, I mean, that's something that we did for Hike, for example, together with the people from the Beams division at CERN, right? In order to do the studies that we did for the Hike proposal. I know that, you know, I was involved also in the other proposals for doing the beam dump facility at in ECN3, and that's all done with, you know, these Fluka simulations. Yeah.
Yep.
Maybe it's a trivial question, but I was wondering, now that you have these CAD files input, does it mean you can take anything like the snowman, STL files that you get for 3D printers and these kind of things, and you just can pass Fluka on it? Is that simple?
It's almost plug and play, yes. Almost.
All right. Okay. So explain a little better. Here we were doing this during the training week. So was the idea to learn a little bit of these tools. And that's why I check the homework.
Right. Excellent. Okay.
on the textbook, actually. Because some professional did. He was kind enough to go back to the school level for us and produce these things. But at least personally, I would like to have a look at these references from back then, because there is probably, the overall lesson is probably there. As you said, maybe the normalization is not accurate. Definitely.
I think that here, like for example, it would be interesting to if you wanted to just look at this and directly compare to what is, what was assumed for example, the count production my talk, or for example, in any of the documents like the the hike proposal, for example, or anything like that, then you would need to make a angular cut, right? So this is,
Yep.
I think this is the, I mean, so you angular and momentum cut, but maybe it depends, because for the when we were talking about neutral kaons, there weren't really any momentum cuts because you can't select the momentum, right? But there were angular cuts, right? And then if you're talking about the charge kaons, then they're going to be, you'll have a much larger angular byte, but maybe they're usually, you look at a monochromatic beam, so you would want to know a very small momentum byte, right? So the
Yep.
phase space is important, right? In terms of the angle in this case, yeah.
Yep. No, I fully agree. And this is why I like Fluka, because I change one parameter in the cards and I get it for free. So so I fully agree with you. This is just to show a plot, let's say.
So I don't know if this exercise can be really brought much further at this point. For us, said it was really a training objective, and maybe raise some interest in kaon physics by producing kaons. I think I still have some questions personally, but maybe are very basic one on how NS2 works. So maybe we can defer that for later. But I don't know if in the room there is more to say at the moment.
The exercise, seeing how you can use the proton beam of a muon provider for a demonstration for different physics, and using this kaon experiment as a benchmark that needs maybe slightly different things is a very useful exercise. Maybe we can bring this exercise as a slightly more advanced step to like, okay.
The kaon source business, yeah, sure. I mean, if I had time, I would definitely redo this plot, which I had not done with myself. Try to put, and maybe ask Matthew to explain once more why the cut in the angle is done, and this correlation kaon pion with the angle, etc. It's basic kinematics. I don't want to do it in public.
Okay.
So let's keep it. But yeah, the part I think maybe hotter is how to change the gray part of the front end in the muon scheme, in the source scheme. If there is basically a way to run this as a, let me say, parasitic kind of experiment where we know for the muon beam, basically every now and decide to do kaon physics. I would like to know at the very least. Then, okay, other people will decide. Actually, before I was thinking, this sounds like the kind of discussion you should have with directors of a lab. But they're not here. But yeah, we should put.
Sure. Mhm.
Absolutely, absolutely. That's the nice part where I learn something. Then I have to learn why can physics get cancelled every 10 years. I
Yeah,
learned,
well, that's interesting.
from this BNL experience, and then CERN. Actually, I
Mm-hmm.
was shocked that already at the NA62 level almost.
Yes, yes, yeah, that's definitely true. I mean, like I said, it's important to acknowledge at least in terms of chaos physics, well, first of all, there was much more interest in the world scale, right? If you go back to the year 2000, you had very active programs in the United States and in Europe and in Japan. And
You mean in
and
Keon
US
or
was, and
in
US
general?
was really active. Like I said, you had two labs that were interested because you had, Keon physics being done at Fixed Target at Brookhaven with, experiments well, I mean, Copio was part of RSVP, so that also had the predecessor, I can't remember what it was called, the predecessor to Mu2E was there as well, right? Was in part of that program. So that was Copio, right? And then you had 787, and then you had at Fermilab, you had a higher energy proposal both for a charge count experiment, which was called CKM, and a neutral count experiment, which is called Kami. So there were 4 experiments that were planned, and the only one that ultimately went forward was 787-949, and that was canceled 1/5 in after 12 weeks of a 60-week run. All right, so I mean, it was really really a lot of really a lot of ideas and a lot of people interested, and they were very discouraged, I would say, right? And this is on the U.S. side, right? Fortunately, things, the investment was a little bit more continuous. It wasn't as big, and it wasn't, as multifaceted, but it was more continuous in Europe and Japan. And that kept the things vital until now, basically, right? And then we're just left with just the Japanese program, which is a very important program, but it's very focused on one measurement. That's the problem, is it doesn't have the breadth that was part of the field before.
Yes, I think we can keep discussing with coffee mug
Absolutely.
in our hands. It was very instructive, so I would like to thank Daniele for joining.
Thank you for inviting.
Yeah, thank you all for being here.